Welcome, everyone. Arim is going to be telling us about supersymmetric W-algebras versus W-algebras. Take it away, Arim. Thanks.
Thank you for the introduction, and thank you for giving me this opportunity to give a talk in this seminar. As you can tell from the title, the two main objects of my talk would be supersymmetric W-algebras and W-algebras. Okay. W-algebras were first introduced in physics, in particular two-dimensional conformal field theory. The structure of W-algebras are mathematically described in the language of vertex algebras. Considering their supersymmetric analog, we can obtain supersymmetric W-algebra. So supersymmetry means in physics, it means a kind of map that sends boson to fermion and fermion to boson. And this phenomena was characterized mathematically as supersymmetric vertex algebras. So even though these two algebras are based on a little bit different theory, there is a conjecture by Madsen and Ragusea that these two algebras are actually isomorphic up to tensor products of free fields. So in the recent joint work with Naoki and Arim, we could prove this conjecture in the cases of principal W-algebras. So I'll explain the result in this talk. So first, I'll explain the notion of supersymmetric vertex algebras, which form a mathematical background for the study, and give some examples of them. And next, I'll introduce you supersymmetric W-algebras. And next, I'll explain what the conjecture means and give the brief proof of the conjecture in the principal cases. So first, for those who are not familiar with vertex algebra theories, I'll briefly introduce what vertex algebra is. So roughly speaking, it's a superalgebra determined by infinitely many products. So we'll denote the products by parenthesis n, we'll call it nth products. So these nth products satisfy some axioms. I didn't specify here, they satisfy some complicated axioms, but the point is that they are not commutative and are also not associative. And also vertex algebra is equipped with an even derivation called partial or just translation operator. And this even derivation satisfies this relation, which is compatible with the nth product. So the commutator with the nth product is related to some constant multiple of n minus 1th product. So in this talk, I'll draw some picture like this. So I'll write down the nth product in vertical way, and we'll write the commutator with the translation operator and the arrow going up. So whenever I draw some picture like this, you can just think of it as some vertex algebra structure. Yeah, among this nth product, this minus 1th product, first product is important. So it has a special name, which is normally ordered product, and we denote it by AB with colons on both sides. In this talk, most of the vertex algebra that we'll consider will be freely generated. So I'll give you a brief explanation for the freely generation. So we'll consider finally many elements, A1 to AM. And if the vertex algebra V is actually equal to the span of differential ordered monomials with variables AI, then we'll call V freely generated by AIs. Here I used ordered monomials because the product is given by the normally ordered product, not the usual product of variables. Okay. So on this vertex algebra, we're considered the notion of supersymmetry. So in the introduction, I said that in physics, supersymmetry is a kind of map that sends boson to fermion and fermion to boson. Mathematically, bosonic fields are usually interpreted as even elements in the superspace, and fermionic fields are usually interpreted as odd elements. So supersymmetry should be interpreted as an odd endomorphism on superspace. And moreover, we want to think about supersymmetry on a vertex algebra particularly. So we want to add some condition to make it compatible with the nth product and the translation operator. So we'll call an odd endomorphism D a supersymmetry if it's an odd derivation with respect to all nth products, and if its square is equal to the translation operator. So if a vertex algebra is equipped with n supercommuting supersymmetries, we'll call it a large n equals to n supersymmetric vertex algebra. So in this talk, we'll just consider large n equals to 1 case. So we'll just simply omit n equals to 1 and just call it supersymmetric vertex algebra. So in a supersymmetric vertex algebra, we can draw a picture like this. As I said earlier, these vertical lines are considering the nth product of elements in the vertex algebra. So here I drew nth product of an, and I drew the nth product of the element d of a. And the arrows going up are the commutator with the translation operator, as in the earlier. And in the supersymmetric vertex algebra, we also have the supersymmetry G, an odd endomorphism, and we can also consider the supercommutator with D. Then one can easily see that since this odd derivation for nth product, this D goes diagonally in this way. So basically, it seems that the supersymmetry D sues two different fields by taking its commutator. So in a supersymmetric vertex algebra, to emphasize that two elements A and DA are coupled as a superpartner, we often write the nth product of A as A n/1, and the nth product of dA by A sub A/0. So as in the vertex algebra, we often use a different notation called lambda bracket. So in the vertex algebra, the lambda bracket is defined by a finite linear sum by introducing an even formal variable lambda. So this lambda bracket is basically a linear sum whose coefficient is given by the nth product between two elements. Here, the lambda to the n is just a divided power. Just lambda to the n divided by n factorial. And here we only denote the positive nth product. And the well-known fact is that if a vertex algebra is freely generated, then its information is all included in just the lambda bracket between the free generators. Of course, in supersymmetric vertex algebra, we can just use the lambda bracket because it's basically just a vertex algebra. But to emphasize that it has a superpartner for each element, we can write in this way. So we introduced an odd formal variable chi, and we write lambda and chi as a tuple and write it in a large lambda. And the large lambda bracket is sum of the lambda bracket between dA and B, and chi times lambda bracket between A and B. So, and also in supersymmetric vertex algebra, their structure can be fully described by the large lambda bracket if it's freely generated. So we'll see the first example of supersymmetric vertex algebra, the simplest but the most important example, which is Nouveau-Schwarz vertex algebra. So for a complex number C, the Nouveau-Schwarz vertex algebra is a vertex algebra freely generated by two elements. One of them is L, even, and the other one is odd element G. And the lambda bracket relation between them is given as follows. You can see from the first line that the lambda bracket between L and itself is equal to the Virasoro relation. And you can see from the second line that G is primary of conformal weight 3/2 with respect to this Virasoro element. And this L appears in the lambda bracket between G and itself. And note from this lambda bracket relation that the zeroth product of L is actually equals to the translation operator of the vertex algebra. So in this Newell-Schwarz vertex algebra, we can take the map D as a zeroth product of the odd element G. Then for any element in this vertex algebra, one can easily deduce that it's actually an odd derivation by the property of a zeroth product. And also, since the L appears in the zeroth product between G and G, one can compute that the supercommutator of D and D is actually equal to 2 partial, which implies that the square of D is equal to the translation operator. So from this relation, we check that this D commutes the conditions for it to be a supersymmetry. Therefore, this Newell-Schwarz vertex algebra is a supersymmetric vertex algebra with a supersymmetry D, which is equal to G0. And in particular, we saw that the subalgebra generated by L is isomorphic to the Virasoro vertex algebra. Actually, this example is very special since the supersymmetry is actually given by the zeroth product of particular element. So we can generalize this notion further before we move on to the next slide. In this example also, we can draw a similar picture. So in this case, D of G is actually equal to 2L, the 2 times of the Virasoro element. So the picture looks like this. Here is the nth product of G, and here is the nth product of 2L. Okay, so we can generalize this special circumstance into the notion of superconformality. So a supersymmetric vertex algebra is called superconformal if there is an odd element G, such that 1/2 times D of G is a conformal vector, I mean the Virasoro element. And if this L and G generate a Newell-Schwarz vertex algebra, and the supersymmetry D is equal to the zeroth product of G, then we call it a superconformal. And in a superconformal vertex algebra, we call G a superconformal vector. Okay, now we'll see more examples of supersymmetric vertex algebra. To see more examples, I'll introduce you the notion of universally enveloping supersymmetric vertex algebras. So in the vertex algebra theory, universal enveloping vertex algebra is a kind of thing that's analogous to the universal enveloping algebra of the Lie algebra. So in a vertex algebra theory, we have the notion of Lie conformal algebra, which is just an affine analog of Lie algebra. So it's a C partial module in those with a map, which we denote by just lambda bracket as before. And this map satisfies skew symmetry and Jacobi identity as a Lie bracket does. And it also satisfies sesquilinearity, which states a compatibility between this lambda bracket and the partial. And if we are given a Lie conformal algebra, we can immediately consider the corresponding vertex algebra like this. So the vertex algebra is given by this space spanned by the normally ordered products of the elements in the R. So this space has a vertex algebra extending the structure of the lambda bracket. And we'll call this VR the universally enveloping vertex algebra of R. So we want to make this picture in a supersymmetric setting. So in a Lie conformal algebra, we can similarly define a supersymmetry. So in the vertex algebra, a supersymmetry was an odd endomorphism, which is odd derivation for all nth product, and its square is equal to the translation operator. So we can define this the same way in the Lie conformal algebra. But here is the only difference is that the Lie conformal algebra only has a positive nth product. So this all means that just positive n. So if a Lie conformal algebra is equipped with a supersymmetry, we'll call it a supersymmetric Lie conformal algebra. So fortunately, without the need to introduce new notion, if we are given a supersymmetrically conformal algebra and we just forget the supersymmetric structure and consider its universal enveloping vertex algebra VR, then it immediately has a supersymmetric structure. So this supersymmetry D is an extended version that came from the supersymmetry in R. And this D is just extended by making it an odd derivation for the normally ordered product. So with this universal enveloping algebra, we'll introduce examples. The first one is supersymmetric affine vertex algebra. So we'll first consider an abelian or a simple Lie superalgebra with an even supersymmetric bilinear form. And we'll denote the parity reversed version of it as G bar. Then we'll define a supersymmetric Lie conformal algebra as follows. So it's a space given by the direct sum of G and G bar, and we have a free action of the partial. And we have a further central element whose where the partial acts on K trivially. And the lambda bracket between these elements are given like this. You can see from the first line that this lambda bracket resembles the Lie bracket of a affine Kac-Moody algebra, or just a affine vertex algebra, if you're familiar with it. And the lambda bracket between A bar and B is given by the Lie bracket action. And the lambda bracket between A bar and B bar is given by just constant the central element multiple of the bilinear form between them. And we can define the supersymmetry D on its space like this. It sends just A bar to A, and it kills the central element. Since D square is equal to partial, you can immediately see that D of A is equal to partial of A bar. Then the supersymmetric affine vertex algebra of level K is defined by the universal enveloping of this Lie conformal algebra, quotiented by K is equal to K plus H check. So here H check is the dual Coxeter number of G. If G is abelian, H check is just zero. So from this lambda bracket relation, you can see that in the first line, the vertex algebra generated by these A's are actually isomorphic to the non-supersymmetric affine vertex algebra of level K plus H check. So I wrote it in this way. And in the third relation, you can see that the lambda bracket between A bar and B bar are just bilinear form. So it's isomorphic to free fermion vertex algebra. But you can see from the second relation that actually these two subalgebras are not commuting with each other. But there is one way to amend these elements A to commute with the free fermion parts, and that modification cancels this H check level part. So in turn, if we choose that modified generators, we can see that this supersymmetric affine vertex algebra is actually isomorphic to non-supersymmetric one tensored with free fermion, and the levels of two are the same. And the next, before we move on, this supersymmetric affine vertex algebra is actually superconformal for non-critical level. So the formula for this superconformal vector is explicitly known by Katz and Todorov, and it's written like this for a dual basis of G. And with respect to the superconformal vector, every A bar are primary of conformal weight 1/2, and D of A bar, which is simply A, is not necessarily primary, but is of conformal weight 1.
Arim, sorry, I forgot what superconformal means. This is going to be G.
Yeah,
It's going to play the role of G. Okay, thank you.
yeah, yeah. So if you apply D of G, it's something like Pearsall element. Okay. So actually, there's one more sign-twisted version of supersymmetric affine vertex algebra. So actually, those two algebras are isomorphic, but there's not fixed convention yet, I think. So so we often consider the supersymmetric affine vertex algebra with sign terms included in it. Okay, the next example is supersymmetric Heisenberg vertex algebra, which can be directly obtained from the previous one. We'll first let H be an abelian the algebra with the symmetric invariant bilinear form. And you can recall that in vertex algebra theory, Heisenberg vertex algebra is actually isomorphic to affine vertex algebra associated with abelian with some fixed level. We can define similarly here. So the supersymmetric affine vertex algebra associated with this abelian space and level 1 is called the supersymmetric affine supersymmetric Heisenberg vertex algebra. So if we write down their lambda bracket explicitly, the lambda bracket between H1 and H2 is equal to the usual lambda bracket of Heisenberg vertex algebra. And the H1 bar and H2 bar, their lambda bracket is just a bilinear form. And in this case, because H is abelian, and H1 bar and H2 commute with each other. We'll denote this supersymmetric Heisenberg vertex algebra by pi hat H. And one can easily see this relation that this is isomorphic to the tensor product of usual Heisenberg tensor with the free fermion. The next example is supersymmetric charged free fermion vertex algebra. So we'll consider N to be a finite dimensional vector superspace and N star its dual. And we'll consider 4 superspaces isomorphic to N, which will denote phi N, and N bar. This N bar, it's parity reverse space of N as in the earlier case, and N star, and N star bar. And we'll consider the Lie conformal algebra generated by the direct sum of these 4 spaces. And we'll give the lambda bracket relation these elements like this. So we'll only let the unbarred elements be non-trivial and barred elements be non-trivial. So if we are given 2 unbarred elements, they're given by FA, and we're given barred elements, they're given also by FA, but the order is different. And the supersymmetry D on this space is given like this, like sending phi F bar to phi F and sending phi sub A to phi A bar. Then the supersymmetric charge free fermion vertex algebra is defined by the universal enveloping algebra of this Lie conformal algebra. So to understand it more easily, we'll just consider the case when N is just a one-dimensional even vector space. Then you can see that phi F and phi A are actually even elements satisfying these relations. So these two generate a beta gamma system. On the other hand, phi A bar and phi F bar, they are parity reversed. So they're odd and satisfying these relations. So they generate BC system. So when N is a one-dimensional even vector space, this charge free fermion vertex algebra is isomorphic to beta gamma BC, where the supersymmetry sends B to beta, while it sends gamma to C. For remark, if when is an one-dimensional odd vector space, the charge free fermion vertex algebra is also isomorphic to beta gamma BC, but in that case, the supersymmetry is in the reverse way. Like it sends beta to B and it sends C to minus gamma. And this example is also super conformal, which was studied very recently. Actually, this one has pretty many super conformal vectors, but I chose one of them, which was the simplest one. So one of the super conformal vectors is given by this. And with respect to this tau, it's U alpha star is primary of conformal weight 0, and U sub phi sub U alpha is primary of conformal weight 1/2. So if we take another super conformal vector, we can change their conformal weights. Okay. I think we're ready to define supersymmetric W-algebras now. So to define supersymmetric W-algebras, we consider a Lie superalgebra containing an OSB12 subalgebra. So OSB12 Lie superalgebra is spanned by 5 elements, E, H, F, and EF. And this large E, a large H, a large F, they form an SL2 triple. And this small e, small f are odd elements. And these two elements satisfy some Lie bracket very similar to this supersymmetric picture. So in particular, the square of the adjoint action of E is actually equal to the adjoint action of a large E. So this looks very familiar, right? It's like sewing the two fields in the supersymmetric Berg's algebra. Okay, so when given a finite simple Lie superalgebra with an OSB12 subalgebra, we'll decompose G into the direct sum of eigenspaces as usual. And this I is given by the eigenvalue with respect to the adjoint action of X, which is the half of H. And we'll assume that G is equipped with a non-degenerate even invariant bilinear form. And we'll let it normalized by E/F is equal to 1. Then the supersymmetric W-algebra is defined in this way. So we'll consider a BRST complex, CK n equals to 1. So one part is the supersymmetric affine Berg's algebra that we saw earlier. And the other part is the supersymmetric charge for fermion associated with n, when n is the direct sum of positive eigenspaces. Here, the supersymmetric affine vertex algebra is defined in a sign-twisted way. I think if we use non-sign-twisted way, then this D and other elements would contain some non-pretty constants. But anyway, in this complex, we'll consider an even element given by D, which looks very similar to the one that we consider in ordinary W-algebras. The one thing different is that we consider the bilinear form with an odd element F, not with the large F, the even one. Okay, if we consider this D and it's 0, 0's product, which is the zeros product of D of D, then its square is equal to 0. So we'll use this D00 as a differential in the complex. So the supersymmetric W-algebra is defined by taking the cohomology with respect to the complex and D00. So if you're not familiar with this BRST things, it's okay. The important things are their properties. So I'll explain the key properties of this algebra. So the first thing is that this supersymmetric W algebra by nature has a supersymmetric Burix algebra structure. In the complex CK, they already had a supersymmetric structure because each component has a supersymmetric. And one can easily check that this D supersymmetry actually commutes with the differential. So the supersymmetry in the complex actually induces the supersymmetric structure on the W algebra. And the next is that we can regard this supersymmetric W algebra as a vertex subalgebra of an supersymmetric affine vertex algebra. I didn't explain much here, but this can be done similarly to the W algebra case by taking building blocks in the complex. And the next important thing is that this supersymmetric W algebra is actually freely generated by these elements, omega vi bar and d of omega vi bar, where vi are bases of kernel of at small f. Yeah, and the next thing is that it's also superconformal, and the superconformal vector is given like this. So the omega is a superconformal vector in the supersymmetric affine part, and tau tilde is some superconformal vector in the supersymmetric charge per fermion part. This tau tilde is different from tau that I introduced earlier. Yeah. And if we add here the partial of h bar, we get the superconformal vector. And with respect to this vector, all of the generators have conformal weight determined by the degree of Vi inside G. So if Vi has eigenvalue minus Mi, then the corresponding generators has conformal weight 1/2 plus Mi, and this D image has weight 1 plus Mi. So for example, if we consider OSP 1-2, then the corresponding supersymmetric W algebra is the most simplest one, because OSP 1-2 is the smallest Lie superalgebra containing OSP 1-2 subalgebra, obviously. So as I said earlier, this Lie superalgebra is spanned by these 3 even elements and these 2 odd elements. And here, large F is the only element contained in kernel of at F. So this supersymmetric W algebra is freely generated by omega F and D of omega F. And then in this case, we can explicitly write down how the generator looks like. And you can see that this omega F actually contains F bar in its linear part. So also by considering this eigenvalue of F with respect to a joint action of H, one can compute that this omega F has weight 3/2 and D of omega F has weight 2. And this one looks very familiar because this is the same as we saw in Newell-Schwarzschild algebra. And actually this supersymmetric W algebra is isomorphic to the one that we saw before. Here I didn't specify C, but C should be some function, some rational function with respect to decay. And next, if we consider SL21, we can see we can also see how generator looks like. So SL21 is spanned by 8 elements. So here in this part, it's isomorphic to OSP 1-2, and it contains extra 2 odd elements, E tilde and F tilde. And here, if we choose large E, large H, large F, and E tilde and F tilde, and these 5 elements also generate another OSP 1-2 subalgebra. And here we also have extra even elements U, which comes from Lie bracket between E and F tilde or E tilde and F. So in SL21, we have 2 elements in kernel of at F, which are large F and F tilde. So this is freely generated by these 4 elements. And you can see that if we write down the explicit generators, it contains f bar and f tilde bar as a linear term. Okay. With this minimum amount of properties of supersymmetric W-algebras, I'll briefly explain the conjecture about the relation between supersymmetric W-algebras and W-algebras. To compare these two objects, I'll briefly recall the properties of W-algebras. So we just saw that supersymmetric W-algebras are defined when G contains OSB1, 2, and it's a supersymmetric vertex algebra freely generated by these two elements associated with basis of kernel of at F. In comparison to these, W-algebras are defined when G contains an SL2 subalgebra, and this W-algebra is freely generated by elements associated with kernel of at large F. There should be a more profound reason why those two elements are related, but in this talk, I'll just compare the number of free generators in those two objects. So, namely, I'll compare kernel of at large F and kernel of small f. Okay, we'll consider G containing OSB1, 2, and here the large F is related to F in this way. It's -1/2 times the bracket of small f and small f. So using the adjoint action of the OSB1, 2 subalgebra, we'll decompose G into the direct sum of irreducible OSB1, 2 representations. Then the number of these irreducible components will be equal to the size of kernel of at small f. And further, if we consider the SL2 subalgebra, the action of the SL2 subalgebra, we'll be able to measure the size of kernel of at large F. One can see that in any non-trivial OSB1, 2 irreducible representations, it decomposes as direct sum of two SL2 irreducible representations whose dimension difference is just 1. So in this case, it's 4-dimensional plus 3-dimensional, and it's 3-dimensional plus 2-dimensional. And if there is any trivial OSB1, 2 representation, then it would be immediately just a trivial SL2 representation. So one can see that these black dots are actually the elements, extra elements that are contained in kernel of at large F, but not in small f. So one can say it in this way. So for each non-trivial representations, one can associate two elements in kernel of at large F. But that's not true in trivial cases. Trivial cases just 1-to-1. But recall from the properties of supersymmetric W-algebras, regardless where this VI is contained in trivial representation or not, we just assign two generators. So this supersymmetric W-algebras obviously has more generators than W-algebra does, and the number of extra elements is equal to the number of trivial representations in these decompositions. So, yeah, and also, if we measure the conformal weights of these generators, one can easily see that those extra generators should have weight 1/2. So weight 1/2 fields should always be free fields. So we can say that for any non-critical level, supersymmetric W-algebra is isomorphic to non-supersymmetric W-algebra tensored with free fields, where the number of free generators is equal to the number of free irreducible modules in the decompositions, which can be restated in this way. I just use G natural, which is the centralizer of OSP1, 2. So this is the conjecture, and it looks very promising if we just look at this picture. But in general, I'm not sure how the proof will work. But for principal cases, we could prove this conjecture. In particular, if we take principal odd nilpotent, it implies that the F is also principal in G. And in this case, the centralizer is 0. So if you modify this conjecture, then in principal cases, this conjecture suggests that the supersymmetric W-algebras are actually isomorphic to non-supersymmetric ones. So from now on, we'll only consider principal cases, and we'll just omit F, small f and large f. We'll just write down in this way, just WKG. Okay. Yeah. In the recent training work, we could prove that this actually works in principal cases. So in the last session, I'll explain you the most important feature of supersymmetric W-algebras that were used that contributed in the proof of this theorem, which is free field realization of supersymmetric W-algebras. The motivation of free field realization of supersymmetric W-algebras comes from the non-supersymmetric W-algebra theory. So first, free field realization basically means an embedding of a conformal vertex algebra into free field vertex algebras, such as Heisenberg vertex algebras or Fermion vertex algebra, etc. So free field realization makes it easier to work on them because W-algebra is quite complicated, but free field vertex algebra is comparably simpler. So in non-supersymmetric W-algebra theory, their free field realizations were well known. So in 1991, Fagan and Frankel showed that principal W-algebras associated with Lie algebra can be embedded into a Heisenberg algebra when the level is generic. And the generalization of this fact into Lie superalgebras were proven by Naoki in 2017. But in this case, the realization was inside Heisenberg tensored with neutral-free Fermion vertex algebras. So the realizations listed here are all given by the kernel of screening operators, which give us tools to investigate the image of these realizations. So I wanted to generalize this theory to supersymmetric W-algebras. But in this case, I embedded into a supersymmetric Heisenberg vertex algebra. So I could show that for a generic level, a supersymmetric W-algebra of level K embeds into a supersymmetric Heisenberg vertex algebra associated with the curtain subalgebra H of G. In fact, this map was equal to the supersymmetric mirror map, which is given by the projection as in non-supersymmetric theory. Recall that the supersymmetric W-algebras could be embedded into supersymmetric affine, and we can just simply project this element into curtain part. Then it gives us a supersymmetric mirror map, and this was identical to the map that I found. And also this realization could also be given as a kernel of screening operators, but to explain what the screening operators are, I'll give you I'll explain you about the supersymmetric Fock modules of supersymmetric Heisenberg algebras. So recall that the supersymmetric Heisenberg vertex algebra had these lambda bracket relations. So the first one was same as the Heisenberg. The barred element and unbarred element commute, and the barred elements were free fermion part. And this lambda bracket can be rewritten in the supercommutator of the nth product of HIs. which are like this. So I will take this Lie brackets and consider the Lie superalgebra spanned by this nth product. Then the supersymmetric Fock module is defined by the HH module, having the highest weight vector alpha. So we'll first take alpha in the dual space of H, and we'll let alpha be even or odd vector. And the corresponding supersymmetric module is defined in this way. The positive nth product act trivially on the highest weight vector, where the barred element acts trivially for all positive, and the unbarred element only acts trivially when it's strictly positive. And the zeroth product of H act as a constant multiple, giving us alpha H. And the all negative nth products act freely on this space. So if you're familiar with non-supersymmetric Fock module theories, then this supersymmetric Fock module is just a tensor product of two Fock modules, one for Heisenberg and one for free fermion.
I just want to make sure that the H here is just the H is in the even, the all even, or
H is all even because we are taking
so H stars are in the odd degree or also in the even. So that you have H and H bar. Which one is even? Which one is odd?
I think alpha is all even.
Oh, even. I see. You
Yeah.
said respective odd, so I wasn't sure.
Yeah, alpha is all even, but the vector can be regarded either even or odd.
Oh, for the highest weights.
Yeah, for the highest weight.
Okay, yeah, thank you.
Yeah. Okay. Yeah, so even though we define the supersymmetric Fock module as a least superalgebra module, but it turns out to be actually a vertex algebra module if we regard if we just forget the supersymmetric theory and regard the supersymmetric Heisenberg as a vertex algebra. So in this talk, we'll fix the notation. So we'll denote this pi hat minus alpha over nu like this. So if alpha is some odd root, then we'll let the highest weight vector be even with the reverse parity. If the alpha is an even root, then we'll let the highest weight vector odd. Okay. Here nu is just a square root of k plus h, just some constant. Yeah. Okay, if we use these supersymmetric Fock modules, then we can write down where the screening operators goes from and goes to. Okay, so this peripheral realization is actually given by the kernel of screening operators, where its screening operator is associated with simple roots alpha I, and its domain is supersymmetric Heisenberg, and its range is the supersymmetric Fock modules. So this pi hat are the parity of the highest weight vector is fixed as in the earlier. Yeah. So if we I didn't give a proof here, but if we just acknowledge that this is true, then the proof for the conjecture in the principal cases is quite straightforward.
So Arim is the intersection of all those kernels?
Yeah,
One
yeah,
for each alpha I? Okay.
Yeah,
Gotcha.
intersection, yeah. Sorry, I should have written down that. Okay, the idea for the proof of the conjecture is that it just used the peripheral realization of principal W-algebra. So it was proved by Naoki that it's realized as an intersection of kernel of screening operators inside the ordinary Heisenberg tensored with neutral free fermion. And you can compare one by one. So this look different. This operator looks different, but the domain is supersymmetric Heisenberg and Heisenberg tensor neutral free. And the range is supersymmetric Fock module. And in the bottom, it's Fock module tensored with free fermion. So one can easily see that there are isomorphism between the domain and the range of screening operators. And under these isomorphisms, the screening operators are exactly the same, which gives the proof of the conjecture. Okay, yeah, this is the end of my talk, and thank you for your attention.
Thank you so much, Arim. Any questions for Arim? Please feel free to unmute yourself and ask. I'll ask Arim. So what, how difficult is it if the nilpotent is not principal?
If it's not principal.
So I'm guessing it's still open, right? If the, oh, let me maybe
Yeah,
stop
it's
the
still
recording.
open. I think even in principal cases,